Hello students, welcome to my YouTube channel Easy Mathematics. In this video, we come to discuss about decomposition rule to find chromatic polynomial. In our last video, we come to know that how to find out the chromatic polynomial. But by using decomposition rule, it is much more easier to finding out the chromatic polynomial for any given graph. So, how to find out the chromatic polynomial by using decomposition rule or decomposition principle. Let V1 and V2 be two non-adjacent vertices in a graph G. Let G dash be a graph obtained by adding an edge between V1 and V2. Let G double dash be another simple graph obtained from G by fusing the vertices V1 and V2 together and replacing sets of parallel edges with single edges. So what we will do initially? Let us do with an example, then we will understand better. Suppose any graph is given, this one. In this graph, we consider any two vertices, let it be V1 and V2, which are non-adjacent. We should consider only those vertices which are non-adjacent. So if this one is a given graph, then here V1 and V2, these two are the non-adjacent vertices which we can consider. Using these two vertices, we will create two graphs from this graph. First graph should be created by joining these two vertices which are not adjacent. That means this one, this is called the G dash. How to create this one? The same graph, only these two should be added because it is not added in the given graph. So in this way we create G dash. Again G double dash should be created by merging these two vertices. These two are non-adjacent vertices. Now we create G double dash by merging these vertices V1 and V2. So if we merge V1 and V2, then what happens? So the edge V3, V2 should be merged with V3, V1 because now V1 and V2 have the same vertex. So if we do so, then V4 remains as it is, then V3 as it is, and for V1 and V2 should be merged. And accordingly, these two edges should be merged and these two, that means this one and this one, if coming to from V3 to V1, then these two are the parallel edges now. So instead of writing these parallel edges, we just consider any one edge. So finally, after joining these two, that means after merging these two vertices, we get this one as the graph. So this is our G double dash. So any graph is given, from there we find out which are the non-adjacent vertices. Any one pair we consider initially. After that, in the first step, we just add V1, V2, that means add these two non-adjacent vertices by joining one edge, and we will create one graph that is called G dash, and by merging these two vertices we will get another graph which is termed as G double dash. After doing this one, we will say our requirement for the chromatic graph of this graph. Our requirement is to find out the chromatic polynomial for this graph. So this is the notation for the chromatic polynomial, that is Pn G comma lambda. So it is n is the number of vertices, G is the given graph, and lambda is the polynomial in lambda. So this one we will find out by adding these two graphs, chromatic polynomial. So this one is the chromatic polynomial for this graph and this one is the chromatic polynomial for this graph. Just look, in the G dash, the number of vertices are same as the G. But in G double dash, the number of vertex is one less than the G because one vertex is merging in the another vertex. That's why we will write down in this way. This is our decomposition rule. So now, while we are going to find out the chromatic polynomial for any given graph, in this way we separate it into two graphs. After separating in this way, we will observe that this separated graph or these two created graph are complete graph or not. If they are not a complete graph, that means there is a provision to add more edges. That means there are more non-adjacent vertices present. So we again decompose further these two graphs and try to find out all the graphs as a complete graph, the decomposed graph as the complete graph. So if we look these two, then this one is a complete graph because 3 vertices, 3 edges, so this is a complete graph. But this is not yet a complete graph. So this one again we should decompose, and this decomposition should be like this one. From this one we have this V2 and V4. These two are the non-adjacent vertices. So in the next decomposition we should add V2 and V4. So we will find out G1 dashed, and again we should merge these two. If we merge these two, then what happens? V2 and V4 becomes now the same vertex. V2, V4 same vertex means V3, V4. This edge should be merging with V3, V2. And here the V1, V2, this edge, V1, V4, this edge should be merging into the V1, V2. So that here after merging in this way, we will find out this one as the another decomposition, so that we will create these two graphs. So this is the, now look, this is a complete graph, this is a complete graph, and this one is also a complete graph. So finding out all those, what we will do, this one is decomposed again into these two. So this one means we can write the chromatic polynomial for this graph plus the chromatic polynomial for this graph. That is the chromatic polynomial for this one and the plus of the chromatic polynomial for this one. Now why we decompose it into the complete graph? That is because we know that the chromatic polynomial for a complete graph is very easy. If it is a third order, that is it is a graph with 3 vertices, then its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2 if there are 3 vertices. If there are 4 vertices, then here one more factor should be included. So in this way we can find out the chromatic polynomial for any complete graph very easily. That's why we take this decomposition rule to convert a given graph into the different parts of the complete graph, so that we can find out the chromatic polynomial very easily. So this one is also called the fundamental recurrence theorem, fundamental reduction theorem. So we can say the recurrence terminates in a collection of complete graphs. So this is a recurring process. Once we decompose, then again if required we decompose. If these are not complete, then again we should go further for the decomposition. So this is a recurrence process, and this recurrence process will terminate while we collect all the complete graph. So in this way the decomposition rule will work. Now after decomposition, how to find out the chromatic polynomial? For that, with an example we should follow it. So using decomposition rule or decomposition theorem to find the chromatic polynomial of the following graph, we should have this following steps. So initially this one is the given graph, and that should be decomposed into these two parts. This is G dashed and G double dashed. We know how to decompose these two. According to these two non-adjacent vertices, we compose this one, and after adding these two or merging these two vertices, we find out this one. Similarly, as this one is not yet complete, so it should be decomposed further. So this further decomposition leads us to this graph here. These two are the non-adjacent vertices, and depending upon that we will decompose these two. After this entire decomposition, what we will say that the chromatic polynomial for the given graph should be equals to the chromatic polynomial for G dashed, that means this one, plus the chromatic polynomial for this one. But the chromatic polynomial for this one, that is this one, means it is the decomposition of these two, means these two, the chromatic polynomial for this one and the chromatic polynomial for this one. So finally we will find out that the chromatic polynomial of G is equals to this one plus this one plus this one. So we just substitute accordingly all. We will find out that the chromatic polynomial for this graph, this is a graph with 4 vertices and it is a complete graph. So its chromatic polynomial should be, it is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 plus of its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2. So that we have right here. And for this one also, it is a complete graph with 3 vertices and its chromatic polynomial is same as this graph. So that if you write down this one even, then we will find out this one. So these two are the same terms. So if we add these two, then we will find out 2 into this one. And from these two terms, we can take common lambda into lambda minus 1 into lambda minus 2. After taking this common, this part will be remaining. And from here, it is the 2 only remaining. So if we simplify, we will find out this one leads us lambda minus 1. So if we multiply all those, then we will find out the lambda to the power 4 minus lambda 4 into lambda cube plus 5 into lambda square minus of 2 lambda, which is the chromatic polynomial for the given graph. We can verify that this is the chromatic polynomial or not. We know that this digit will verify that the how many number of edges are given in the given graph. So here it is the 4. So in our given graph, let us count that how many edges are given. So it is 1, 2, 3 and 4. So it is true. So this one is the chromatic polynomial. Anyway, so next here, if this one, suppose the graph is given for which we want to find out the chromatic polynomial, then we can do one thing, that we can do this one minus of this one. That also can be done. So this one, for if we want to find out the chromatic polynomial for this G-dashed graph, then it should be find out by P4, that means the given graph G minus of this one. We just immediately calculate the chromatic polynomial for this graph. So this one, and the chromatic polynomial for this one, it is the chromatic polynomial, that is lambda into lambda minus 1 into lambda minus 2. So that if we write in this way, then we can find out the chromatic polynomial for this one directly. So now its chromatic polynomial, if we calculate, then we will find out that its chromatic polynomial is this one. And just observe here in this graph, the total number of edges are 1, 2, 3, 4, 5. So in the chromatic polynomial, this coefficient is 5 only. So this is the chromatic polynomial for that one. One more example, by using the decomposition rule, we are supposed to find out the chromatic polynomial for this one. So this one, again here we will find out that the non-adjacent vertices are present. So we should decompose it into two parts. So by this decomposition, so just look, if we consider these two vertices, then we should add in the first graph and we should merge these two vertices in the second graph. So after merging, we will find out this one as the graph. So both of them are non-complete graph. So that we should decompose further. So for this one, the non-adjacent vertices, now we can consider it is these two vertices. So that we have to add here. So we should add these two and we should merge in this second graph. So after merging these two vertices, if we merge, then we will find out this type of graph. Just look how to merge. This vertex will be merging here. So accordingly, this edge merging to this one, this edge merging to this one, and this edge merging to this one. So finally, we will get this one as the graph. For this one, it is again a non-complete graph, so that we should have these two as the non-adjacent vertices. So in the decomposition, we should add these two vertices by an edge, and after merging these two vertices, we will get this one as a graph. So now this one is a complete graph, this one is a complete graph. So further decomposition is not required for them. Here this one is a non-complete graph, and this one is again a non-complete graph. So that we go for the further decomposition. So now this decomposition means from here, the adjacent, these two vertices are non-adjacent. So we should add these two vertex by joining one edge. So after joining this one, now it becomes a complete graph. And after merging these two vertices, we will find out this one as a graph, which one is again a complete graph. For here, these two vertices are non-adjacent, so that we should join these two by an edge. And after joining this one, we will find out a graph which is a complete graph with 4 vertices. And by merging these two vertices, we will get this one, which one is again a complete graph with 3 vertices. So finally, we should add the polynomial for this one, plus the polynomial for this one, plus polynomial for this one, plus chromatic polynomial for this one, and plus these two. So 1, 2, 3, 4, 5 and 6. This total 6 graph for, we should add the chromatic polynomial. This one is a complete graph with 5 vertices. this one is a complete graph with 4 vertex. This one is also the complete graph with 4 vertex. This is a complete graph with 3 vertex. This is a complete graph with 4 vertex, and this is a complete graph with 3 vertex. So we have one complete graph with 5 vertex, total 2 complete graph with 4 vertex, and total 3 vertex with complete graph with 4 vertex, and total 2 graph with complete graph with the 3 vertex. So accordingly, if we add these 3, then we will find out the chromatic polynomial for the given graph should be this one. This is the chromatic polynomial with 5 vertex and a complete graph. There are 3 such graph with 4 vertices which are complete. So this one is of their chromatic polynomial, and 2 such graph with 3 vertices which are complete. So their chromatic polynomial is this one. So if we now simplify, then we will find out that we just take common lambda into lambda minus 1 into lambda minus 2 from all this, because everywhere it is common. So after taking common, we will find out this one, and after simplification we will get this one, and finally we will get this one as the chromatic polynomial. So this is a chromatic polynomial of G. Hence the chromatic number also we can find out from here. We will know that if we substitute the lambda values as 1, 2, 3, 4, then for which minimum value of lambda, we will find out that the chromatic polynomial giving the non-zero value, then that particular lambda value is the chromatic number. Here we will find out that if we substitute lambda is equals to 3, then it is a non-zero value providing, so that the chromatic number for this given graph is 3, and this is the chromatic polynomial. So using this decomposition theorem, we can find the chromatic polynomial for the cycle and the wheel. In our last video, we will have that the chromatic polynomial of a cycle and a wheel. But how to prove that we will not have done over there. So the chromatic polynomial for the cycle is this one, and the chromatic polynomial for the wheel is this one. So these both of them can be proved by using the decomposition theorem. So if you know about the decomposition theorem properly, then you can easily prove these two formulas for the chromatic polynomial. So it is very obvious that for few standard graphs, we have the chromatic polynomial initially. Likewise, the complete graph, the null graph, the tree, the bipartite graph, and the cycle and the wheel. So if we have initially the known graph, then directly we can substitute the chromatic polynomial for those graphs. So okay, let us do one more example for this using decomposition theorem. So this one is a given graph, and our requirement is to find out the chromatic polynomial for this given graph. So just we observe initially the given graph. In this given graph, if this particular edge will be absent, then the graph becomes a tree. Is it not? So if this edge will not present, then it becomes a tree. And if it is a tree, then we know what is its chromatic polynomial, because any tree for, we know the chromatic polynomial is lambda into lambda minus 1 to the power of n minus 1, where n is the number of vertices in the tree. So what we should do? Here, instead of decomposing this one, what we will do? We consider the graph without this edge, so that the graph, let it be this one. Now we should decompose this one. So now if we decompose and we assume that these two are the two non-adjacent vertices, then its decomposition should be, if we add these two by an edge, then this one, and if we merge these two, then we will find out this one. So now look, our requirement is to find out the chromatic polynomial for this graph, so that we can find out by subtracting the chromatic polynomial of this graph minus of this graph. Now this one is a tree, so its chromatic polynomial is lambda into lambda minus 1 to the power 5 minus 1. 5 is the total number of vertices. But its chromatic polynomial is again unknown, because it is not a complete graph and it is not even a tree. So now what we can have for this graph, if this edge is not present, then it is again a tree. So that what we will do, for this one we consider and we decompose, then we will find out this one and this one. After merging these two vertices, we will get this one, and after adding by an edge, we will get this one. So this one and this one same, so that its chromatic polynomial should be this one minus this one, and this both are the tree now. So its chromatic polynomial is lambda into lambda minus 1 to the power 4 minus 1, because there are total 4 vertices given, and its chromatic polynomial is lambda into lambda minus 1 to the power 3 minus 1. 3 is the total number of vertices in this graph. So that we can find out the chromatic polynomial for this one, and that is this chromatic polynomial minus of this one. So we will get the chromatic polynomial for this one also. So now if we find out the chromatic polynomial for this one, then it should be this, the chromatic polynomial for this graph minus the chromatic polynomial for this graph. And after simplification we have done. So here is the calculation. So the chromatic polynomial for the given graph should be find out by means of this one minus of these two. So if we simplify, then we will find out it is lambda to the power 5 minus 5 into lambda to the power 4 plus 10 into lambda to the power 3 minus 9 into lambda square plus 3 of lambda. So from here we can easily say that the chromatic number for this given graph is 2, because if we substitute lambda is equals to 2, then it is a non-zero value providing. And one more thing, the number here, the coefficient for the second highest power of lambda is 5. So there should be 5 number of edges given in the graph. So let us check once more. How many edges are here? It is the total 5, and yes, it is 5. So just according to the polynomial, we can have the total number of vertices in the graph is 5 number. So hence this is the chromatic polynomial for the given graph. So I hope you understand and you enjoy the video, because I think it is my personal opinion that the chromatic polynomial, finding out the chromatic polynomial is much more easier by using the decomposition theorem. So for any graph, you can find out the chromatic polynomial by using this decomposition theorem. If you use it properly and if you apply it is properly, then you can find it out very easily. So hope for the best. Have a nice day and wait for the next video. Thank you.